This is a pretty difficult type of problem. So we're just going to jump in and do it together. How does that sound? Okay, wonderful. So it says a lab test for the detection of a certain disease gives a positive result 5% of the time for people who do not have the disease. The test gives a negative result 0.3% of the time for people who do have the disease. Large-scale studies have shown that the disease occurs in about 2% of the population. So the question is, what is the probability that a person selected at random would test positive for the disease? First thing that we need to do is define all of our variables. So, what variables are we looking at?
Positive test results?
Okay, so I'm going to say P is misleading. Let's not use P, because P normally stands for probability. How about T? T is going to be a positive test result. Okay, you don't need to define negative. T complement will be negative, a negative result. Okay, there's one more variable that we need to define. So what else is being talked about besides testing positive or negative? False positive. Read the last sentence.
Population.
Nope.
How much their tests?
Nope.
Disease.
The disease, yeah.
Especially looking at disease.
Yeah. So we're talking about you either have the disease or you don't. You take a test, you either test positive or you test negative. Okay. So it says, what's the probability that a person selected at random would test positive? So we are looking for this. Now we need to convert everything that it says in the problem to probability notation. So it says a lab test for the detection of a certain disease gives a positive result 5% of the time for people who do not have the disease. Okay, so what that looks like is given that you don't have the disease, given you don't have the disease, the probability that you test positive is 5%. Okay, the test gives a negative result 0.3% of the time for people who do have the disease. Okay, so given that you do have the disease, the probability that you get a negative result, so that's T complement, is 0.3%, so that's going to be 0.003. And lastly, it says large-scale studies have shown that the disease occurs in about 2% of the population. So the probability of having this disease is about 0.02. Okay. What I notice here is that these two variables are complementary. These two variables are complementary, and that this is the given. So that's how I know that I need to do this new process. So if these two variables are complementary, these two may or may not be complementary, and the given is given to us. So what we're going to do is we're going to draw a tree diagram. Whichever single probability you are given denotes how you're going to make the tree. So our first two branches are going to be based off of this, because it's the only single probability that we've been given. These are conditional. Okay, so your tree is going to go like this. For each person, you either have the disease or you don't have the disease. No other option. Probability that you have the disease is 0.02. Therefore, what's the probability of not having the disease? 0.98. Okay, now let's say that you have the disease. There are two options. You have the disease and you take this test. Either you test positive given that you have the disease, or you test negative given that you have the disease. Those are the only two options. Same thing for our lower branch. If you don't have the disease and you take the test, you still can test positive given that you don't actually have the disease, or you can test negative given that you don't have the disease. Okay, so then that goes to here. The probability of a positive given that you don't have the disease. So you don't have the disease, testing positive, this is 0.05. So this number here then is 0.95. Okay, then going here, given you have the disease, the probability that you test negative is 0.003. So you have the disease, testing negative is 0.003. Likewise, up here is 0.997. Okay. Now your tree goes horizontal like this. Any of the branches that are not horizontal, so that go like this, sum to 1. So these two are always going to sum to 1. These two are always going to sum to 1. These two are always going to sum to 1. If I take this probability and I multiply it by this one, I get an AND. So this is the probability of T and D. So when you multiply the previous two branches, you get an AND. That comes just based off of the conditional formula. So then when I multiply these two, I get P of T complement and D. So this is going to be P of T and D complement. This is going to be P of T complement and D complement. Okay. I need somebody with a calculator to actually multiply this for me. So I'm going to do 0.02 times 0.997. 0.01994. Okay, and then 0.02 times 0.03.
6.0006. So just says 6 times 10 to the negative
0.0006.
You need to review your scientific
But I
notation.
But I did something.
You said 6.0006.
No, I said 0.0006.
Okay, 0.98 times 0.05.
0.049.
0.049. And then lastly, 0.98 times 0.95.
0.931.
0.93.
See how it is.
Okay. Now these four probabilities should all sum to 1. Whew. Okay. Now we're looking for the probability of testing positive. That was the whole question. What's the probability if I choose someone random that they're going to test positive? If you test positive, one of two things happened. Either you tested positive and you had the disease, or you tested positive and you didn't have the disease. These two numbers come from the table that we just did. So testing positive and having the disease, this one right here, is this probability. So that's going to be 0.01994. And then testing positive and not having the disease is 0.049. What do you get when you add them?
0.06894.
0.0689. So for this test, the probability that you test positive is 0.0689. How do we feel about this?
Is it on Monday's quiz?
Nope. Your quiz on Monday does not have conditional probability on it. There's a part B, isn't there?
Yeah.
Yeah.
Yes. Okay, do we have any questions on this? No. Okay. here's how I knew that I had to draw the tree. Let's say you didn't know and you just used that P of T and you tried to figure it out by hand. This is what you would get. So we had. Can I see your notes? Anytime that you're given a conditional probability, try to set up the formula and see where it takes you. This gives me the probability of T and D complement over the probability of D complement. This one will give me the probability of T complement and D over the probability of D. This one is nothing. So we were looking for the probability of testing positive. That doesn't show up in any of these formulas. So when you hit that roadblock, you need to go to the tree. Okay. Look at part B. Okay. What is the probability that a person selected at random who tests positive for the disease? So, given that the person tests positive, what is the probability that the person does not actually have the disease? So that's D complement. So this is going to be the probability of D complement and T over the probability of T. That's just the conditional formula. Probability of T is what we selected in part A, so 0.0689. And the probability of D complement and T is in the tree. So D complement and T. So this right here, it's an and, it's just written in the reverse order. So 0.049. I don't know what that is.
0.711.
Yes, Brooke?
Nothing.
Okay.
Reading it wrong.
Okay, so that's the answer to part B. Which to me sounds very counterintuitive. Look at that probability. If you test positive, the probability that you don't have the disease is 0.711. Isn't that very surprising? Wouldn't you expect it to be so much smaller?
Yeah.
Like 5% or something? Okay. That's why, have any of you ever had to take a drug test for a job or for anything else? Yeah. So if you ever have to take a drug test and you test positive, the first thing that they do is they test you again. Because there's such a high rate of like false positives for this very reason. That's why I think that conditional probability is kind of tough, because it's very counterintuitive. A lot of times you end up with an answer that doesn't really make sense. In this case, we got the right answer. It just goes completely against what you would think intuition-wise. Okay.